I hope you're all having the greatest of evenings. I'm Mr. H. Thank you for joining me for this video. We're looking here at a very interesting and unique phenomenon, the telescoping series effect. You know what an old-fashioned naval telescope looks like. It is in a compressed format. You open it up and it expands out. You can take it back. Why am I bringing this up? Because the telescoping series effect is very much similar like this. You expand your telescope out for your required action. When you're done, you bring it back to its normal position, which is in a very contracted state, and the series example behaves in a very similar way. The point that you want to remember, the telescoping series, what we're looking here, is made up of telescopic sums, which are your finite partial sums, in which, as you will see, the pairs of consecutive terms will cancel out. The pairs of consecutive terms cancel out and you're only left with two items at the end, the first item and the last item. The very first and the last item. Everything in between, all the intermediate terms, consecutive terms, they cancel each other out. Much like a telescope, you're expanding it out, doing your stuff, then you're compressing everything back and getting to your end result. That's exactly what you will see play out with this single example that I'm going to present to all of you. But you have to see what we're looking at. N equals 0 up to infinity, a series 2n factorial divided by n plus 2 factorial. You would want to rewrite it as this. Push the 2 out. N equals 0 up to infinity, n factorial or n plus 2 factorial. Think about how the factorial expressions can be simplified. You have n factorial in the numerator, and then think about what a factorial is. You're looking at product of consecutive terms where each term is decreasing by 1. So you're looking here at an n plus 1. Then you're looking at an n, then n minus 1 onwards. But this part right here is equivalent to n factorial. You're looking at this cancelling out with this. Essentially what you have left with is 1 over n plus 2 times n plus 1. That's what remains. So essentially everything boils down to this particular rule, 2 n equals 0 up to infinity, 1 over n plus 2 and then n plus 1. And by doing that setup over there, we made great progress. Because now what we want to do is look at this part right over here. If you were to look at this 1 over n plus 2 and n plus 1, you were to think about what was the sum of partial fractions that gave you this. You can do this. You're looking here at a over n plus 2, a procedure which is your partial fraction decomposition is equal to right here, the 1. But I'm going to say 0n plus 1. You do your partial fraction decomposition procedure. The reason why I'm doing all of this will become very evident for you. A into n plus 1 plus b into n plus 2 is equal to 0n plus 1. Open this up. You have an plus a plus bn plus 2b is equal to 0n plus 1. Your linear terms are a plus b is equal to 0. These are your linear terms, the n terms. And then your constant terms are these. A plus 2b is equal to 1. You can do elimination. You have a plus b is equal to 0. A plus 2b is equal to 1. Eliminate them. You'll have minus b is equal to minus 1. Therefore b is equal to 1. And then a must equal to minus 1. We've determined we have minus 1 and 1. And that helps us determine what the partial fractions was. And you know all of this. What was the partial fractions that gave us this item right over here? And now we know what that item was. It was minus 1 over n plus 2 plus 1 over n plus 1. This right here represents that. Now, if you're looking at your series has become n equals 0 up to infinity, this. But I want to write this in a good way because I want to write the positive term first. And I want to flip these things around. I'm looking here at a 1 over n plus 1, you know that, minus 1 over n plus 2. All I did was flip them around, but I've done it by erasing and writing. That's all I've done. Now if you were to expand this out in terms of a series, only this part, what do you really have? If n is equal to 0, what are you looking at? You're looking at 1 over 1 minus 1 over 2. That's coming here from n equals 0. Then what item are you getting when n is equal to 1? Then you're having 1 over 2 minus 1 over 3. And then when n equals 2, what are we getting? You have 1 over 3 minus 1 over 4 and on and on. That's exactly what we have. This expands to that. But look at this. As I told you, the partial sums, your telescopic sums, the consecutive pairs cancel out. These cancel out. Such that all which will remain is your very first term and the very last term, your a-nth term and the a0 term. What is your a0 term? It's 1 over 1. a0 term is equal to 1. A-nth term will eventually equal to a 0. All of this right here by means of the series is equal to a 1. Now you're seeing the telescoping series effect come into play. Our entire rule, I'm erasing this part for you right here. Our entire rule has become something very wonderful. Our series rule. Our series rule has now eventually become this 2 n equals 0 infinity. We have 1 over n1 minus 1 over n plus 2. It has become this 2 times this 1 right over here. Because this 0 is meaningless. 1 plus 0 is a 1. And essentially our series is equal to a 2. The entire series right here, this particular series from 0 to infinity, if you were to do its sum, the sum of the series is equal to 2. It's convergent. And that telescoping series effect has come into play. Some will say telescoping, some will say telescopic. It's either or, it doesn't matter. It's a matter of semantic. But this right here is what I wanted to show you. A highly interesting phenomenon which comes into play when you bring in the partial fractions and you get these into play. It doesn't happen with everything, but it happens in some cases. When it happens, you have a very wonderful result, and I've shown you that. A real finite convergent value. That's all what I wanted to show you in this video. Thank you for watching.